some basic question of linear algebra as a review. First question, based on subspace. The question is, consider W1, W2, W3 be the three distinct subspace of R10 such that each Wi has dimension 9. Let capital W equal to W1 intersection W2 intersection W3. Then we can conclude that option 1, W may not be subspace of R10. Option 2, dimension of W less than equal to 8. Option 3, dimension of W greater than equal to 7. Option 4, dimension of W less than equal to 3. Here first option has indicate W may not be subspace of R10. Notice here W equal to W1 intersection W2 intersection W3. And we all of us know the theorem, intersection of arbitrary many subspace is always be subspace. But in the first option indicate W may not be subspace of R10. So by this theorem we can tell option 1 is a wrong option. And option 2 indicate dimension of W less than equal to 8. Option 3 indicate dimension of W greater than equal to 7. And option 4 indicate dimension of W less than equal to 3. For this I will use one nice theorem, and the theorem is, here I will use this theorem, dimension of W1 intersection W2 less than equal to minimum of dimension of W1 comma dimension of W2 and greater than equal to maximum of 0 comma dimension of W1 plus dimension of W2 minus dimension of V. This is the theorem. Here I will use this theorem. Okay. Now let's see these three options. Here in the question has given W equal to W1 intersection W2 intersection W3 and all the question about dimension of W. For this theorem, I will consider W1 intersection W2 equal to W dash. That means W equal to W dash intersection W3. Then I will use this theorem. Here at first I will find the dimension of W bar. Then I will find dimension of W. And dimension of W bar means obviously we have to find dimension of W1 intersection W2. Here I will use this theorem to find the dimension of W1 intersection W2. By this theorem, given dimension of W1 and W2 is dimension is 9. So this would be minimum of 9 comma 9. And this is less than equal to dimension of W1 intersection W2 and greater than equal to maximum of 0 comma dimension of W1 is 9 plus 9 and dimension of the vector space is 10. Okay, that means this would be dimension of W1 intersection W2 less than equal to minimum of 9 comma 9 and this is greater than equal to maximum of 0 comma here 8. Okay, but in the question has indicated on W2 W3 are three distinct subspace of R10 whose dimension 9. Each Wi has dimension 9. So if we consider dimension of W1 intersection W2 equal to 9, this is thus not possible because W1 and W2 are distinct subspace of R10 and given dimension of W1 equal to 9 and dimension of W2 equal to 9. That means obviously W1 contain 9 linearly independent eigenvector and W2 contain 9 linearly independent eigenvector. Then obviously dimension of W1 intersection W2 would be obviously greater than equal to 8. This is 9 cannot, dimension of W1 intersection W2 equal to 9, this is not possible because given W1 and W2 are two distinct subspaces in R10. That means if W1 contain such element A, B, C, D, E, F, G, H, then obviously since this is W1, obviously W2 contain at least one of them would be different element, and since W1 intersection W2 means the common element of both W1 and W2, but if we consider dimension of W1 intersection W2 equal to 9, then this does not imply W1 and W2 contain distinct element. So dimension of W1 intersection W2 equal to 9, this is does not possible. Means obviously dimension of W1 intersection W2 would be greater than equal to 8. That means dimension of W1 intersection W2 would be greater than equal to 8. Have you understood this concept? Now we have to find actually dimension of W, and I have find dimension of W bar. Now we have to find dimension of W bar intersection W3. Then here to find dimension of W, here I will use also this theorem. This would be minimum of dimension of W bar comma W3 and greater than equal to maximum of dimension of W bar plus dimension of W3 minus dimension of V comma 0, and this would be dimension of W less than equal to minimum of, here this would be 8 comma 9, and this would be maximum of 8 plus 9 minus 10 comma 0. That means this would be dimension of W less than equal to 8, and this is greater than equal to 7. Now see the option in the question has indicate dimension of W greater than equal to 7. Option 2 indicate dimension of W less than equal to 8, and option 4 indicate dimension of W less than equal to 3. So, since dimension of W greater than equal to 7, that means option 3 is the right option. I hope my all viewers have understood this option clearly. Okay? Oh yeah. Now I will see one basic question of linear algebra which had come CSIR NET September 2022 exam. The question is, consider U and V be the subspace of R cube defined by U equal to set containing the element x, y, z belongs to R cube such that 2x plus 3y plus 4z equal to 0, and V equal to x, y, z belongs to R cube such that x plus 2y plus 5z equal to 0. Then which of the following statement is true? Option 1. There exists an invertible linear transformation T from R cube to R cube such that Tu equal to V. Option 2. There does not exist any invertible linear transformation T from R cube to R cube such that Tu equal to V. Option 3. There exists a linear transformation T from R cube to R cube such that Tu intersection V not equal to singleton set 0, and characteristic polynomial of T is not product of linear polynomial with real coefficient. Option 4. There exists a linear transformation T from R cube to R cube such that tu equal to v and the characteristic polynomial of t vanishes at the points 1. Actually, first option, there exists an invertible linear transformation t from r cube to r cube such that tu equal to v. This is actually based on extension theorem. As a review, just recall the statement of this theorem. The statement of this theorem is every linearly independent subset of a vector space can be extended a basis. Actual concept is, consider the set v1, v2, vk be a linearly independent subset of n-dimensional vector space V. Then we can always find vk plus 1, vk plus 2 up to vn such that the set v1, v2, vk, vk plus 1, vk plus 2 up to vn is a basis of the vector space V. In linear algebra, there exists a nice theorem. If there exists a linear transformation from V to W and consider beta 1 be the basis of the vector space V and beta 2 be the basis of the vector space W, then there exists a linear transformation from the basis beta 1 to beta 2. If this is surjective, then obviously there exists a linear map T from V to W which is injective. Also, if there exists a linear transformation T from beta 1 to beta 2 which is injective, then obviously there exists a always linear map T from V to W which is surjective. This type of concept I will use here. Here notice U be such type of subspace and V be the such type of subspace, and we have to find there exists a linear transformation T from R cube to R cube such that Tu equal to V. Notice here dimension of U equal to 3 minus 1 which is 2. Also dimension of V equal to 3 minus 1 which is actually 2. I hope my all viewers have understood. Since dimension of U and V equal to 2, both dimension is 2, and we have to find there exists an invertible linear transformation such that Tu equal to V. For this, I will use one linear transformation which map basis to basis, and obviously the basis of U and V would be such type. One basis always would be common in both case U and V, because there exists always be one common solution in this subspace, because dimension of U plus V equal to, you all of us know this theorem, this is equal to dimension of U plus dimension of V minus dimension of U intersection V. Okay, in U and V always there exists one solution which is common, because by this theorem we can tell this is easily, because since here the both dimension of U and V is 2, so this would be 2 plus 2, 4. But here obviously U and V be the subspace of R cube, so always there exists one vector in U intersection V. That means in the intersection always there exists one common vector. Basis would be such type. Consider the basis of U would be B1, B2, and if B1, B2 be the basis of U, then the basis of V would be such type. There exists always one vector always would be common, so this basis would be such type 1, B3. Okay, and the concept of extension theorem is, since this is the basis of the subspace U. So obviously these two vectors would be linearly independent. Also, if we add one vector gamma 1 in the base in this vector, then by extension theorem we can tell this is be the basis of R cube. Similarly, by extension theorem, if we add one vector also here, beta 1, beta 3, here gamma 2 also, this is the basis of R cube. Have you understood this concept? I hope my all viewers have understood. Then we have to find exists an invertible linear transformation T from R cube to R cube such that Tu equal to V. By this concept, we can tell there exists a linear transformation T from R cube to R cube which map basis of R cube to basis of R cube. I have got few minutes ago. This is the basis of R cube and this is also basis of R cube. So we can define one linear transformation which map basis to basis. And this type of linear transformation is obviously such type Tu equal to V, because this is the basis of U and this is the basis of here obviously beta 1 basis of V, and this type of linear transformation obviously invertible. So option first is a right option. Exists an invertible linear transformation T from R cube to R cube such that Tu equal to V. This is obviously right option. And since option 1 is a right option, that means option 2 obviously wrong option. There does not exist any invertible linear transformation T from R cube to R cube such that Tu equal to V. And option 3 indicate there exists a linear transformation T from R cube to R cube such that Tu intersection V not equal to singleton set 0 and the characteristic polynomial of T is not product of the linear polynomial with real coefficient. Here the question has indicate Tu intersection V is not equal to singleton set 0. For this, we all of us know this theorem. Dimension of U plus V, that means dimension of Tu plus V. We all of us know this theorem is dimension of TV, Tu plus dimension of V minus dimension of Tu intersection V. And since I have got dimension of V is 2 and also dimension of Tu would be 2, because I have got dimension of U is 2, that means U contains two linearly independent vectors, and always linearly independent vector map linearly independent vector to linearly independent vector. So dimension of Tu also would be 2. So dimension of Tu would be 2. That means this is equal to 2 plus 2, 4. But this is the linear transformation which map from R cube to R cube. So obviously always there exists at least one vector in this intersection. So this concept is right concept. Always Tu intersection V not equal to singleton set 0. Have you understood this concept? I hope my all viewers have understood this concept easily. And such type of linear transformation would be such type. Here the characteristic polynomial is x minus 1 times x square plus 1. Have you understood this concept? Means option 3 is the right option. And option 4 indicate there exists a linear transformation T from R cube to R cube such that Tu equal to V, and the characteristic polynomial of this linear transformation vanishes at the point 1. Obviously this type of linear transformation always exists. Characteristic polynomial vanishes at the point 1 means obviously that imply eigenvalue of this linear transformation is 1, And this type of linear transformation would be such type T of beta 1 equal to beta 1. Because subspace U and V always beta 1, this basis always be common basis. So when there exists a linear transformation T from R cube to R cube such that T of beta 1 equal to beta 1, then we can tell the characteristic polynomial of T vanishes at the point 1. So option 4 is a right option. I hope my all viewers have understood this type of question easily. This is basic but very conceptual question. Okay, well, today I will stop here. In my next video, I will discuss this type of question again, because I have told you linear algebra is very important for higher study. Okay. See you soon. Stay safe and stay positive always. And don't forget to subscribe my channel for more videos. Thank you so much.